Excellent. Well, thanks everybody. And that's a tough act to follow. Thank you, Frida. That's amazing to hear what's happening in Denmark. So hopefully we can keep pace and catch up and learn from all the groundbreaking work that you've done. So we appreciate that. My name is Eberhardt. I'm the Director of Energy Services at the University of California Office of the President, which, for those of you who aren't familiar with the system, we have 10 campuses, 5 medical centers, and then the Office of the President is effectively the central office, not attached to any campuses, but we get the pleasure of working with and supporting all the campuses. So it's really great opportunity to see across all these institutions and what's happening. So today I'm going to be moderating the Resilience session, and I'll share my screen and put up the presentation. And Allie, let me know if you cannot see that. And as Josh mentioned today, we've had a pretty rough last year or two through the pandemic and through, especially in California, through wildfires and other events that have happened that have really changed our perspective on energy and our response to major disruptive events, to put it lightly. And I've also learned that humans are extremely adaptable creatures, and we're just kind of continuing to move forward and making it happen, which is impressive and really great to see across the system, across the state, across the country. And we've just seen things from wildfire, smoke events, how that affects facilities and energy issues, multi-day planned and unplanned outages for universities and critical facilities, pandemic impacts to building occupancy, going from fully occupied facilities to empty facilities, associated HVAC operation to address occupancy, safety around pandemic concerns, and then the complete flip of wildfire smoke issues. So addressing all these things has just been an extreme challenge for a lot of us, I think, across the university space and across, I think, just in general as facilities managers. So we're going to go through some of those issues. And as Josh mentioned, I think it's a really great panel we have today that's going to talk through those items from kind of the macro grid level to the campus level and then the building level. And we have experts in all three of those areas. So I'll introduce them. First, we're going to have David Erne, who's the manager of the Supply Analysis Office here at the California Energy Commission. Next, we're going to have John Onderdonk, who's the Interim Associate Vice President of for Facilities and the Chief Sustainability Officer at one of our sister universities at CalTech, an amazing organization. And then lastly, we're going to have Chris Weyandt, who's our energy management engineer at the Sustainable Berkeley Lab, which is Lawrence Berkeley National Lab, our affiliated national lab with the UC system. So 3 amazing subject matter experts that will take us through, starting from the highest level, moving down to the as Josh mentioned, the nuts and bolts building level. So I'm excited to hear this transition as we move through. So logistics quickly, we're going to have those presentations. We're going to then allow 20 minutes for Q&A. As we did in the previous presentation, please type your questions in the Q&A box. And again, chat is enabled, so please feel free to connect with each other one-on-one as we're moving through the presentation. And so with that, I will turn it over to David. Stop sharing.
Good morning. Let me make sure that I can pull up my slides and then I'll go through the introductions. All right, can folks see that if I switch to presenter mode? Does that help? I can't tell which screen. Can you see the presenter mode?
Yep, we can see it.
Okay. Good morning, everyone. Again, my name is David Erne. I'm with the California Energy Commission, one of the 3 energy institutions in California, and work collaboratively with our California Public Utilities Commission and our California Independent System Operator, and we coordinate to help with keeping things moving on the grid, so to speak. I want to thank Eric for inviting me to present today and give you a high-level overview of what's happening at the state level. Also want to thank Frida for a wonderful presentation this morning, evening for her, and appreciate the ongoing collaboration with Denmark. So we have, the Energy Commission has been working closely with the government of Denmark to help share information about things that they're doing and things that we're doing in California, and how we can try to learn from each other. They are quite further ahead on the offshore wind. And as some of you know, we are going to be embarking in offshore wind now that we've had areas released by the federal government for us to develop in. So our offshore wind is going to be taking off hopefully in the not too distant future. And we've had a lot of conversations about all their experiences with offshore wind and converting it to hydrogen and all of the great things that they're doing in Denmark. So very excited to be sharing that. So let me give you kind of an overview of kind of, as Eric mentioned, what's happening at a high level, and then what the energy institutions are doing to coordinate to try to address some of the challenges that we have in California with the grid. So as he mentioned, climate change is posing a much greater challenge. Is this slide forwarding? Is it, can you see the new slide?
Yep, we can see it. It's a little small, but we can see it advancing.
Okay, I wish I could make it bigger.
Not sure.
Wrong way. Maybe if I move it onto a different screen. That's probably lost. Hold on. Are you seeing anything?
I think we're seeing a section of your PowerPoint application, the top toolbar, but if it's causing a problem, I would just go back to the original small. It's fine.
Let me redo this, close out of the file. For some reason, Microsoft has decided to completely shrink my. Yeah. Okay, let me try again.
There we can see your PowerPoint now.
Is it showing in presenter mode? And
no, just regular mode, but if that is what works, that's fine with me.
All right, well, as long as you can see it. I try to keep the slides, the amount of text small, so I should be able to work through this. So let me talk about some of the challenges we're seeing with climate change in California. As was mentioned, we've had record-breaking heat. Last year, as you may recall, August and September posed some pretty substantial challenges for the grid. We had rolling blackouts in California in August 14th and 15th. And then we also had some near issues in September as well, with temperatures that were extreme. We broke records not only in California, but in some cases west-wide during those heat events. And as you know, that we also had them this year as well. We had multiple days where we had exceeded records in California and the west-wide area. Last year's temperature extremes would be considered about a 1 in 30 year for heat, which is pretty amazing. Where traditionally across the US, we plan our supply for an average year, 1 in 2, and this was a 1 in 30. So you can see where substantial demand resulting from those extreme heats. Drought, also a problem. It's always been cyclical in California, but those drought conditions are getting more severe and longer. We're moving into another phase of that. At least it's looking like another part of that cycle where the drought was pretty substantial this year. NOAA predicts that it's going to continue into next year similarly, and that's west-wide. And then as a result of both of those, the heat and the drought, we have more wildfires. And those, as you can see, can cause quite a few problems, not just for the homes and the people who are in those areas prone to wildfires, but it was already also noted causes cloud cover or causes smoke, which reduces solar generation, but also that smoke can affect things like our transmission system. And earlier this year, a fire up in Oregon, actually the smoke caused them to derate or to lessen the amount of power that we could get from the Northwest. So our imports that we get from our neighboring states can be affected by wildfires, whether they're here in California or in our neighboring states. So the west-wide effects of climate change are real, and we're definitely feeling those as they relate to our grid. Demand going up. I mentioned for drought, obviously, as folks know, our hydro generation has gone down this year. We've seen record lows in places like Folsom Lake, even Hoover Dam, pretty substantial decline in their availability to produce. As I mentioned last year, we had the rotating outages in August. And this, I like showing this graph because it gives you an illustration of some of the changes that we're seeing in our system and the problems that we're having. So if you look at the blue line, that is demand, that's our real demand in the system. And the net demand is you take off solar and wind. And as you can see, as you get further into the day towards the evening, our demand actually goes down, but our net demand doesn't, because of the drop in solar, causes the problems right there in those evening hours. So really from like the 4 to 9 p.m. is a problem, but that where we used to have peaks in the middle of the day, now with solar, the peak issues are happening later in the day, and with solar declining in the evening, we have even bigger problems late in the evening after the sun has set. Wind, as we get more and more wind, that has shown that it can help us in those areas, but we have far more solar in California than we have wind. And so that net peak area is really where we're having some of our problems that we need to address, and ensuring that we have resources available on the grid to help us during that peak time. As a result of those summer issues, the governor asked for the 3 energy institutions to take a look at what caused the problems and identify solutions to fix those problems. And so the 3 energy institutions developed what's called the root cause analysis. And they looked at the issues associated with those August rolling blackouts and trying to determine what had happened. As I mentioned, extreme weather conditions were probably the most substantial, that we had conditions in California that not only were record-breaking, but certainly ones that we don't plan for when we buy supply. Our planning processes need to definitely be improved. Our resource adequacy and other ways that we look at planning for our future have to change. We're planning based on an average year. Those average years were based on what I would consider conditions that we're not seeing now. Climate change is changing. When you're averaging over past years, or we didn't have the impacts of climate change, and you're looking at forward years where you have more climate change, you really need to be thinking about how you plan and plan differently. And there were some market changes that CAISO needed to make to improve the way they were bringing resources onto the grid. As a result of that, there have been a number of changes that were made from all the energy institutions to address that. As I mentioned, the challenges are that we have demand in some cases that is much harder to plan for. And as I also mentioned, we have these supply uncertainties, hydro impacts. And actually an interesting part of the hydro impacts we have in California is not only do we lose generation, but an interesting part, because there is so much water movement in California associated with the state water project, that actually when we have droughts, there's less pumping. So there's actually a little bit lower lowering of their demand, but certainly the lowering of their generation surpasses the lowering of their demand. And what we've also found is we rely on imports, particularly during those net peak times, and those imports are critical. But as there are west-wide heat events, those imports become more challenging and more competitive. And it's unlikely that we're going to have as much, or could have as much electricity coming from all the hydro in the Northwest coming down in California when there are west-wide heat events and that electricity is needed in those states. And so we have to be thinking west-wide about those situations. And as I mentioned before, wildfire impacts on transmissions we've seen both in terms of the impacts to getting the imports and the problems with the transmission lines. And for those of you, I don't have the map on here, but the transmission lines, particularly for those that come from other states, it's pretty hard to come to the major load centers in the state, bring electricity in there from surrounding states without going through high fire threat zones. So all of those transmission lines go through high fire threat zones, and so they are at risk either within California or in our neighboring states before they come to California. So wildfire has a potential more substantial impact than we had previously experienced. So what did that mean? So as we saw problems in the state, issues identified in the root cause analysis. So what that really did was kick in a much higher level of coordination that occurred mostly in 2021 and 2022, but is progressing to move forward over the next 10 years and beyond. So as part of the efforts resulting from the root cause analysis, and what we experienced this year was that the Public Utility Commission authorized the investor-owned utilities to procure more. And so they brought more resources on this summer and next summer to ensure that we're doing well this summer and next summer and provide for those greater demand days. As I mentioned, CAISO made some market modifications so that they can ensure that we have all the resources that we need during the net peak period, particularly. We improved the Flex Alert system. That was a CPUC and CalISO effort. And Flex Alert is the way to voluntarily get reduction. So it's more notification to customers that we're going to have these heat events and try to reduce demand. And Flex Alert has been shown to be successful in bringing demand down during those net peak by customer changes in behavior. We substantially increased the coordination among the three energy institutions so that we are sharing data more routinely and rapidly, having coordination meetings that are happening at a minimum weekly, but oftentimes even within the week to share information about what's going on, getting reports from CalISO about how conditions are faring, how we think in the week ahead things are looking, so that we can coordinate our activities more effectively. And part of that is identifying contingency resources, which I'll talk about in just a second. And then enhancing our forward planning. So CPUC is improving their process for planning for procurement out further in their IRP proceeding to look at greater procurement moving forward. CEC has been doing more analysis of our conditions in the near term, midterm, and long term. And I'll talk a little bit about those, the things that we're doing there to help inform the state and what the conditions might be. As I mentioned, there are always going to be need for contingencies. So when we buy, if you think about it, you think about insurance, you can always buy lots of insurance and you can be overinsured so you never have an outage. And that comes at a cost. And when California has has high rates, we look at trying to balance that. So ensuring that we reduce the risk to the customers, both in terms of outages, but also in terms of cost risk and balancing those. And sometimes there are going to be times where we need contingencies, and those contingencies are perhaps opportunities for some large customers to reduce their demand. So beyond the demand response programs that are currently out there, we can engage with large customers, and Tesla is one of these as an example where they were able to shift their production schedule on particularly problem days to reduce their demand during the net peak and shift their production from one time to another. So we can get large customers to voluntarily work in that area to reduce their demand. Not always the most appreciated, but certainly is an option, is to have large users go on emergency backup generators. Those do produce pollution that we don't want to have, and so we don't want to go to that point, but there are opportunities where we can call on them to do that. And there's also opportunities to, where necessary under an emergency proclamation, we can buy additional temporary generators that we can bring online and put those in place to help reduce the chance of outages. Again, those contingencies are not things that we want to rely on day to day, but we want to have backup opportunities for those situations where we have these extreme heat events to help keep the grid stable and not have to go to rolling blackouts. Let me go into some detail on things that the CEC does. So CEC,
hey, David, just real quick, we want to probably finish up in about 2 or 3 minutes. I think you're just about there. Yep. But thank you for making it all happen, and we're just about there. Thank you.
Okay, thanks for the time check. Appreciate it. So things that we're doing is really helping with the forecast of how things look in the state, both projecting the demand, and this is one of the early main missions of the Energy Commission, was to develop the demand forecast to be used in the state to look at how what the demands are going to be and what we expect them to be under various conditions. And we're enhancing that demand forecast to consider climate change and fold that in to be more effective. And we're looking at reliability assessments. So we're looking at near-term, mid-term, and long-term as identified here, and running different models to try to assess whether we think we're going to have the opportunity for outages and whether the procurements that we have are enough to keep us stable in the long term. We also work with power plants to help improve their performance, and we fund R&D. The R&D projects are helping to inform state opportunities. And before I came to the assessments division, I was in our R&D division. We had major R&D efforts around microgrids, and I'll just point out one here that was one of the award winners for a solicitation I worked on, which is at Santa Rosa College, where they are implementing additional PV, energy storage, and load shed disconnects, all in a part of helping to provide resilience for the university or for the junior college to ensure that they can, first of all, reduce their grid draw and by using energy storage, bring down their peak costs. And then when there is resilience issues, because they are prone to being around wildfires, that they can shed particular buildings as appropriate and be able to draw from the PV and the storage and keep certain buildings operating and no other ones that they can shut down. So it's been a pretty important effort, as well as taking the lessons learned from that and building it into their curriculum. So with that, I will close out and we can move on to the next speaker.
Perfect. Thank you, David. Appreciate that. And we'll transition next to John Onderdonk, who's going to give us the campus view of some of these disruptive events, and we'll have time for Q&A at the end. So please remember to you can type your questions in Q&A anytime.
Good morning, everyone. Hopefully you can see the slide deck here. So as Eric mentioned, I am going to talk about the campus perspective, but I also want to talk about more of my philosophy, our approach at CalTech to resiliency, how we are selling resiliency internally, the strategy for it. So it would be a bit more high level, but all the components that David mentioned are going into our planning and our thought process as we work through what resiliency means at CalTech. When I think about our philosophy, it really revolves around adaptive capacity for me. And really my goal in decision making is to make sure that the decisions I make today are leading to optionality, the flexibility to adapt tomorrow and down the road, right? My concern, or the thing I'm trying to avoid, is that those constraints, the proverbial being painted into the corner approach. So as long as I can set that direction and make those choices today and maintain that adaptive capacity in the future, I think we're going to be in a good spot. So what that means, when I think about resiliency at CalTech, it means that we have a couple of key components. This is the Energy Managers Conference, so I'll spend more time talking about the things later down this list, but I did want to point out that I think the people component, as Eric mentioned earlier, is incredibly important. We've all learned over the last 19 months that human beings are adaptable, and that is the most important part, in my opinion, and cultivating that culture of adaptability and giving the skill set to human beings and people involved in our organizations is the most important way we can adapt and be resilient. But this isn't the psychologists or the HR, program. So I'll focus in on some of the other scenarios or the other layers down below, starting with the scenario planning. Again, the whole point of our master planning is to get us that direction, not the compass heading. So, when you're orienting in the forest, you want to know which way to go in general, but you don't need to go in a straight line to a specific compass point. That is all involved with our scenario and sensitivity planning. Electrification and interconnection. Obviously, I think everyone here understands the importance of electrification. The ability to generate and store and use energy in different ways is far superior from an electrified and interconnected world than sort of centralized fossil fuel based combustion world. Supply diversification is an obvious one as well. I approach resiliency very much from an ecological standpoint. My fundamental training is in environmental science and ecology. And so it's intuitive to me that the healthiest habitats, environments, or organisms in those environments are the ones that are most diverse, have the largest skill set, the largest bandwidth, right, for adaptability. Those are the ones that are going to survive over the long term. And that's really what I'm trying to do with our organization, is look at it from that pseudo biology standpoint and thinking of it as a living organism and how can we maintain its capacity. And the last is that focused on adaptive capacity, which we'll get into at the end of the presentation. So starting off with our master planning approach, this is just a quick overview of what our master planning identified as our major constraints for our utility systems. I think it's no surprise to everyone who's involved in a higher ed institution that our infrastructure is strained. At CalTech, it's redlined, particularly in steam, chilled water, and electricity. Chilled water and electricity much more so. Chilled water was certainly the Achilles heel and is currently today the Achilles heel. We're investing in new capacity. That's only going to become more important as we have more cooling degree days and higher temperatures, longer duration of temperatures, hotter nights, and so forth. So we know that is going to be constrained. This was highlighted to us brutally by the fact that the last two buildings we've had to build on campus all require tens of millions of dollars in infrastructure investment in our central plant and satellite plant to just cool the buildings. So it's clearly not the right way to build a campus and operate and maintain a campus when you're trying to build a brand new building and then you're spending those researchers' dollars across campus on the central plant. It's an extremely frustrating place to be in. Electricity is the same. Legacy infrastructure, lots of challenges on that front. And so starting with the electrical side, this is the very nuts and bolts, boring aspect of resiliency and investment. But I think it's critically important. Not only obviously are you getting rid of end of life equipment or things that are well beyond end of life, you're also reducing risk as far as environmental risk, PCB, limiting PCBs and limiting lead, eliminating the hazardous materials that are in some of the older transformers. You're also getting that connectivity, right? Everyone here understands the connectivity, building intelligence, connection to BMS, SCADA systems is critically important, and the ability to manage, operate, and maintain our facilities. And all of this is helping address deferred maintenance. So when I go and I talk to our board or our administration, these are the type of investments that are required for deferred maintenance, elimination of that, rather than necessarily making us more sustainable or making us more resilient. But obviously it is doing all of those things. It's certainly a win-win-win. Taking a specific look at our newest building, in fact, it's the Chen Neuroscience Research Building, focused on neuroscience and bioengineering. This is the first time on campus where we've created a microgrid specifically for a single building. It was done so because of the research requirements of the building and the general concerns with the risk of having this sensitive research go down. What we did from the microgrid standpoint was develop a tertiary system of supply. We have a Bloom fuel cell that is the primary. And we've had Bloom fuel cells. We have 4 megawatts on campus right now. We've had them on campus for about 11 years, and they have never gone down. Whereas our cogen plant, it's a 12.5 megawatt turbine, has gone down effectively a planned down maintenance every year. Certainly 1 or 2 times it's also gone down throughout subsequent years. So it is a good system, but it's certainly not as stable as a fuel cell. The backup then would be Pasadena Water and Power. Again, a very reliable utility, but certainly has the squirrel in the wire potential, not to mention the fact that there is a single utility line coming into the city of Pasadena from the SoCal ISO grid. So it is a very brittle system when you look at it at a macro scale. And then lastly, this is an interesting one that we stuck with a diesel generator, and this was really not intentional. We didn't want it in our planning, but as we started talking through the city, the officials, the permitting agencies, the users themselves, everyone felt that this boot and suspender diesel generator was the right way to go. So it's very much an add-on, and it's kind of this, I think a perfect example of the change of mindset that is required as we think about these different systems. We're still not quite there yet, so we do have that piece of the puzzle still in place. But ideally, we won't get there with the other 2 pieces in place as well. Moving on to this concept of adaptive capacity and thinking about the laboratories, all of us here are very familiar, I think, with sort of building flexible lab spaces. And this is an example, open floor plan. You're bringing the utilities down from the ceiling. We've been doing this in higher ed for a while, so you will allow the researcher to pivot and do their thing, be flexible within their lab space. And it's worked out very well. These are robust ways to build. The researchers like them. They can be modified. But I think it sort of is somewhat constraining in the sense that it only focuses on the individual lab. So what I'm trying to do is expand this perspective beyond the lab and get into the building and ultimately the campus. So another example of things that we've done here is starting looking outside the lab at these service chases that are aligned with laboratory spaces. And so in this particular one, this is feeding a quantum mechanics laboratory. We have the ability to bring dewars and cylinders of gases through this hallway. We can bring equipment through the hallway to support the lab. We can run new utilities, et cetera. So it works well, but this is obviously taking up prime real estate in the building. And so this is a concern as far as when you look at the cost per square foot or look at the research benefit per square foot, you're taking up this critical space. So we have been moving into catwalks and above overhead service. And I think this is going really well from our standpoint in the sense that we now have the ability to service, maintain these laboratories from above. And particularly this is important when we have the critical laboratories in this drawing. It's showing the Viberia, but it's important for all of our sensitive research that our technicians are not in that space. The researchers, PIs don't want us in that space, right? So we can both do our jobs in our own spaces and support the research that's going on, as well as bring in new service as needed as the lab changes. So that's an important approach, but taking that to the next level of our buildings, this is one of our newest buildings under design, and we're trying to move the utility cores to the perimeter of the building so that you maintain that open floor plan that's very functional and very adaptable. And so from a research standpoint, it makes a lot of sense. Now it puts some constraints on the design team, and the architects certainly are struggling with this because you don't want to just have a block of utility chases glued onto the outside of your building. You have to make it architecturally, aesthetically pleasing. So it does present some challenges there. So we're wrapping this particular building with this facade, the undulating facade, glass facade, to improve the look and feel. But again, form and function are the constant struggle, obviously, when we're looking at architecture. There are also other constraints here, longer pipe runs, higher costs, things like that come into play. But we think that this is the appropriate way to be building buildings to help us with that ability to adapt. And so ultimately, I want to take this perspective of adaptive capacity, maintaining our optionality, maintaining our flexibility down the road, to look at our campus level. And we're all familiar with the app on your phone. You want a new functionality on your phone, you drag and drop that app, it works, you're up and running, and you're good to go. We are far from that at a campus level, but I want to try and build an operating system at a campus level that essentially allows the researcher to plug and play. We're given 9 to 12 months when a researcher is announced to come to CalTech. We're given 9 to 12 months to make that lab happen and support that researcher. They want to land on the ground on day one and jump into their research. And so the only way we can do that is through this plug and play application, building our adaptive capacity to support those quick changes. And that is what resonates with our faculty. That's what resonates with our administration. So that's what I'm talking about when we go in to these meetings and talk about the investment that is needed in our infrastructure to support this operating system, right? And that's resonating with my constituents, the people that I'm talking to. It also clearly has benefits from a sustainability standpoint, a resiliency standpoint, as we're all talking about here, dealing with hot, fire, wildfire issues and so forth that we're all confronting, at least we are in California here. So I think there are multiple wins here, but at CalTech, I'm focused on this adaptive capacity as the approach we're taking on resiliency. So that's the extent of my presentation here. Let me stop sharing. We'll jump over to Chris. Hopefully left you enough time, Chris, and we'll then have some time hopefully for questions.
Excellent. I think we've got plenty of time. Thank you. So I am Chris Weyandt from Berkeley Lab. I manage the ongoing commissioning program for Sustainable Berkeley Lab. And I'm going to talk today about some of the things that we've had to start thinking about since, well, in the past 2 years for several reasons. That have sort of changed our perspective on where we should be focusing our attention, specifically dealing with buildings that are operating at significantly reduced capacity, but have very little shift in our baseline energy usage. So Berkeley Lab is, we're just above UC Berkeley. Down here in the left corner, you can see UC Berkeley. We've got about 140 structures up on the hill here, and maybe 25 buildings that are significant in size. Pre-COVID, we had up to about 5,000 people on our campus on any given day. That went down to 4% when the stay-at-home orders first started. At this point, we're back up to 1,600 people on site, and in-person activities are resuming. Our ongoing commissioning program has been operating for about 5 or 6 years now, and we have made a lot of progress in really getting our laboratory buildings working properly. It's been our main focus. We have a lot of laboratory buildings that use incredible amounts of energy, and we've really gone after optimizing those systems to reduce primarily the amount of natural gas that we're using for reheat in these buildings. We've also, worked in new construction and retrofit projects, and over the years, this has added up to a pretty decent amount of cumulative savings. And this is a look at what our general energy consumption split is across our campus. So we've got about 38% of our energy goes towards laboratory buildings and 11% towards the larger office and support buildings. And so this is really where we've focused our attention, trying to optimize these systems. There's this other 9% up here that's labeled as non-key or unknown. And I said we have about 140 structures. So that's, that little chunk right there is actually quite a few buildings, lots of HVAC systems that can and should be operating on time schedules, but for various reasons may not be operating as they should be. So in the past 2 years, we've got this huge list of new things that we have to think about. And we've talked a bit this morning already about wildfires, and that's had a dramatic impact on us in terms of power outages and also changing the way we operate our HVAC systems to mitigate smoke in the buildings, which is the opposite of what we want to do for COVID-19 respiratory disease concerns, where we want to increase the ventilation rates and keep more fresh air moving through our buildings. We've been running systems longer. We have far less people in the buildings, and people are getting moved around so that they can create more separation. And the biggest one is that we have employees now working in shifts. We also have a lot going on with infrastructure resilience planning, some massive projects, upgrading our underground utilities, preparing us for automated demand response, and trying to get rid of the natural gas consumption in our buildings. But the thing that I'm really focusing on here is what's happened as a result of the pandemic, and just another way of looking at these things I've listed off here. Well, we are using more air for longer periods of time, serving fewer people, and who are occupying more space. And now we don't know when they're there necessarily. I've been in the building automation industry for about 20 years, and as a contractor and as an owner. And most places that I've worked, the schedules for HVAC systems don't get changed very often. I think it happens more frequently at universities and campuses, campus environments, but in general, the schedules in these systems, in my experience, don't get changed unless somebody asks for them to be changed. And this is what really started bothering me when we were watching our buildings, knowing that our site population was just dramatically reduced. So we started going down this path that is in collaboration with quite a few different people. Researchers at Berkeley Lab, researchers at UC Davis's energy department. Basically what we're doing is collecting statistics on Wi-Fi connections from every single building across our campus. And this is a look at one building from a paper that was published a few years ago, where we're comparing DOE reference schedule, this orange line, to the profile of the count of Wi-Fi connected devices in a building. And you can see here, we're looking at 4 different seasons. And for this building, you can see that this expected schedule where people start showing up around 6 a.m., get towards, pretty large increase in occupancy at 8 a.m. Everybody leaves for lunch and then they go home around 6 or 7 p.m. It's not what we're seeing in this building at all. It's shifted dramatically, except for in the winter. Apparently people don't feel like coming in quite as early, and they don't have as much reason to get out early when it's dark outside in the winter. So it's actually, the DOE reference schedule is static over the whole year, but our actual profiles are not. And I can imagine for college campuses, this is far more dramatic when you involve classrooms and students, which we don't have on our site. So this is a diagram showing how we're collecting this information. So we've got over in the building, people are walking around with cell phones, smartwatches, tablets, but then you also have these static devices like printers and machines that are in the building. So not everything is a person. And also, personally, when I walk into my office, I have a laptop, I have a tablet, I have 2 cell phones. So quite a few different devices that I might have when I'm walking into the building, maybe not when I go to lunch. So there's obviously a lot of uncertainty in this information. However, the networks are consistent in every single building across our campus. So because of that, we're able to run a single script that pulls every single device on our network and collects statistics from it. Now there's a library that's publicly available on GitHub under LBNL's Environmental Technology area department, and you have a link down here. The library is called Counting Occupants Using Network Technology, and it was developed by a number of people, but mainly Marco Bertoni and Anand Prakash, who helped us implement this and have also implemented it on several other campuses. We take in data that has a lot of potentially identifying information, but we strip out all of that, anything that poses a privacy concern, and just push the aggregated statistics for each device in each building up to a database. And again, like I said, because this is consistent across every single building, we're now getting a data points for all of those 140 facilities across our campus, instead of just the ones that have modern automation systems in. And for us, that's only a handful of buildings. We have a lot of buildings that are running with automation systems that were installed in the 90s or even the late 80s. And so not a lot of information coming from them. So after implementing that library, and we've been collecting that data for several years, but not actually using it for any operational purposes. It was used to do a couple studies and write some papers. But eventually we got this data into SkySpark, which is our energy management and information system that we use for collecting data from everything across our campus. I do have another acknowledgement down here for Phantom Factory, which is a provider of custom tools for SkySpark, and I did need to use their tool to get this data into SkySpark, but once it's there, we can do all kinds of fun stuff with it. Now, this was actually a project that I did for the capstone for my master's in data science. And so there is a lot of source code and information, papers, reference documents in this GitHub repo here. And because it was a data science program, we had to try all kinds of fancy techniques to figure out how to pull occupancy versus vacancy states out of this data set. And although we ran it across all kinds of neural networks and tried a bunch of different machine learning techniques, what we really came down to was some very basic signal processing. And all we're doing is looking for a large change over a window of this data stream. Because this comes down to a daily question, something that we're looking at day after day, and we really just care to know, are people there or is the building vacant? We can really narrow this down to a problem where we're just trying to optimize the area under this curve against the time span of the day. So this becomes a pretty simple optimization problem. It's just very basic algorithm to actually implement this. There's nothing fancy going on behind the scenes. And as a result, we're able to take that data and compare it to the actual operation of our HVAC systems. So in this chart, we're seeing 2 days worth of Wi-Fi connection statistics here for a given building. The orange line is the actual operating status of the air handler in that building. And the green line is the result of this occupancy inference algorithm that's saying this is when we think people are actually in the building. And you could look at this and you could definitely question that inference. And I won't try to say that it's perfect. And I'll talk a bit more about that later. Obviously this is probably somebody coming in early in the morning and maybe somebody staying late at night. But in general, we get the bulk of the people in the building with this inference. And when we compare those two things, which are two binary states, we end up with 4 potential states for the HVAC system. It's either on or off, and it's either occupied or vacant. 2 of those are what we would consider ideal states when it's off and vacant. and when it's on and occupied. But then there's also these other states that are less ideal. So we came up with this color scheme, converting this to our favorite visualization in SBL, the heat map, giving us a 3-dimensional chart. So if we're looking at a day's worth of time here, and assume this was 3 different air handlers along this scale, we have the off vacant areas in gray. We have the on and vacant periods in orange. So here we have an air handler that's starting up quite a bit earlier than anybody actually arrives in the building. And then in the red, we show the worst case, which is where we've already turned off the HVAC system, but believe somebody's still present. Those are the big things that we have to worry about now with COVID. Before, we used to just say, okay, well, most people should be gone by 6 p.m. So that's when we turn it off. But now we're far more concerned about making sure that air is actually moving when somebody's there. But we don't want to end up with a chart that's all orange, meaning we run the system 24/7 just because we don't know. The final tool that we came up with is a combination of a heat map that's showing a bunch of air handlers across the site. And this involved actually looking at floor plans and figuring out which parts of a building were served by which air handler, and then manually associating those access points, Wi-Fi access points to a given air handler. And then performing that inference day after day. And what we see here is, well, we've got a lot of time that we're not running the HVAC systems, and we believe the building is vacant. We do have some systems that are running 24/7 that technically shouldn't be. They all have their reasons, but we're working on those. We've got here, looks like a system that never turned on, or possibly a data problem. And so this is a pretty useful chart to be able to just kind of click through. I could also zoom out. This is a static presentation, so I can't do it right now, but I could zoom out and look at a whole week or a whole month. And then to provide some actual metrics, basically just taking the durations of each of these states for each air handler and putting those into a chart that can be sorted by any of these 4 columns. So the red zones that we care the most about, if the unit's off and we think somebody's actually there, we can see that this 53 AHU3, 54 AHU3, that's this one. So if I sorted by that list, I could find my biggest health concerns. I could also sort by this one and find, oops, I can't click on that because it's not real. I could sort by the on and vacant time and try to see if I can trim some schedules that units are turning on too early or staying on too late. And then just to provide a final scale to that, looking at the opportunity of these units, it varies dramatically by the size of the system. So we took the one data point that we have consistently for every air handler, which is the size of the supply fan, and multiply that by the number of hours that it was in that state. And so we end up with a metric of horsepower hours, which is a little silly metric, but it does give us some idea of scale where we should be focusing our attention and trying to trim these schedules back. The biggest problem that we have right now with this is not being able to get a good picture of when the building's actually empty. And as I mentioned earlier, there's a lot of devices that may not represent a person there. There's printers. I mean, some buildings have a baseline of like 50 always connected Wi-Fi devices. I think one of our buildings, the lighting system uses Wi-Fi. And so those devices are always on. And because this is an aggregated statistic, we can't really figure out what's going on there. So we have a couple options. One is to actually collect more detailed data from those connections, meaning that we would actually collect device identifiers so we could identify which devices were there all the time versus which devices were only there for part of the day. And that's one thing that we're going to be working on. Another more immediate concern is all the different potential data sources that could be contributing to this inference. So right now we're looking just at the number of Wi-Fi devices, but we've also integrated over the past few months, quite a few other data sources. We got card key data now. Every building has had card key readers installed on the doors, so we can count how many people are swiping in. Can't see who's swiping out, but that does help us sort of add some more robustness to our inference. We also have electric and water meter data, which can be very useful if it's properly sized meters and if it's appropriately submetered. And then the last one is occupancy sensors, which we have only in a handful of buildings. They're newest buildings that have advanced lighting control systems. And the biggest challenge we have here is that in any one of those buildings, at least 10% of those occupancy sensors aren't working properly at any given point in time. And when you're putting occupancy sensors in laboratories, we find vast challenges in trying to get the sensors to see people, but not machines and pieces of equipment that are heating up and cooling down or may have rotating components on them. So we really do struggle with that. But this is part of a much bigger effort that we're going to be working on over the next year. And like I said, it's also something that quite a few other people are working on. The original idea here came from two researchers at LBNL, Alan Meyer, and I think that tomorrow there's going to be a discussion about that research project as well. And actually I have a acknowledgement section at the end here. So I just have a minute or two left here. I'm going to just scoot through this last slide. I'm breaking my own rule and putting text on a slide, something I don't usually like to do. But after we started figuring out that we wanted to adjust schedules, deciding what the set points should be for the setbacks at night, and then getting to the point where we could actually implement them, there's a bunch of other things that kind of got in the way of pressing the button. First, we had to figure out in the laboratories which spaces couldn't have temperature setbacks at night. So there's a lot of spaces where the science going on in that area requires temperature stability, and we don't have that well documented. And it also changes constantly. We have to actually test that the occupant override devices in the building work. If we're turning off an air handler in an office space where we didn't use to turn it off, or we didn't use to turn it off until 9 o'clock at night, that random person who might be there working late needs to know, well, we need to know that when they push the button on the thermostat, the system's actually going to turn back on and provide ventilation. So there's thermostats and occupancy sensors that need to be tested. Then we have to actually tell people that we're changing something, which means that we need to also let them know how to engage the after hours operation. This led us to putting signs next to every single thermostat in these buildings to make sure that people know the air turns off at night, push this button to turn it back on. There's the easy part of actually modifying the BAS, and then there's monitoring to make sure we didn't create new issues. Some buildings just don't warm up in the morning, and so they get overridden and run 24/7. Usually we can solve the warm-up problems, but we have to actually watch for them to make sure we're not creating new comfort issues for our occupants. And then we have to reevaluate those regularly and reevaluate the zone level exceptions to make sure that we don't have so many labs that are outside of their design conditions that they're throwing off all the reset strategies for our larger equipment, larger systems. So there's the acknowledgement page and the end of my presentation. There's a lot of people on here. I'm not going to go through the whole thing, but I do want to point out that there were quite a few LBNL researchers involved in working on this, and it took a lot of effort on behalf of our IT department, mostly to approve the actual collection of this data to make sure that there weren't any significant privacy concerns with the data that we were collecting and using. And so with that, I will end my presentation and we can start questions.
Perfect. Thanks, Chris. That was great. And you just confirmed all roads lead through IT. So that's that hasn't changed. And we're going to take Q&A. So again, encourage folks to add their questions to the Q&A. We have some in there right now. There was one that I think we want to address that would go to John, that was live, that was relating to, again, stepping back, the bigger picture issue that is trickling down to all these presentations are these major disruptive events and how we're dealing with them. And one of the questions was an interest in kind of talking about the challenges and trade-offs of having on-site cogeneration and the resilience associated with that, but then the flip side of the associated greenhouse gas emissions and how to address those in a research and complex critical environment. So John, you wanna take that one?
Yeah, no, absolutely. This is a key issue, and it's been a long-standing issue. I mean, I think everyone who operates a cogen system knows that there are very reliable, in the scheme of things. They've been a very good solution for CalTech in our specific case for a long, long time. But the issue, the challenges, the world is changing around us, right? Obviously, there's carbon emissions, as you mentioned in the question, and being in the state of California, we're regulated by CARB. We have to respond. We have to figure out a way to deal with that. That obviously raises our operating costs and raises reputational risk, raises other environmental risk challenges associated with continuing to operate that system. So the way I approach it is, again, through looking at the optionality down the road. It's very clear to me that the future is moving away from combustion as a source. And so that path, continuing to stay with cogeneration, leads to more constraints, leads to carbon constraints, leads to cost constraints, volatility in natural gas. I mean, we are watching the market right now and trying to make purchases to hedge, but it's a scary market to watch right now. It is very costly right now, but it's also extremely volatile. And so, that is one of the things that makes me sweat a little bit when I'm trying to manage a cogeneration plant. On the flip side, if we were to move to retire our cogeneration, move to offsite or onsite renewables, we have photovoltaics on campus, we have fuel cells on campus, offsite electricity obviously available as well. That maintains more flexibility in how we contract, how we can develop, how we can and work on the supply as well as the storage and end use of that electricity. It also gives us more functionality and flexibility on the heating and cooling side. So we could introduce heat recovery chillers, right, to harvest the heat coming from our buildings, which is one of the things we're looking at, converting to hot water systems and moving away from steam. So all of that gives us better flexibility, and all the modeling that we've done show that the two life cycle costs, long-term costs, are essentially identical. So it's really, the hard part is the pivot, the mental pivot for the people involved, but also then obviously you have to invest in the capital to make that pivot in the short term. And so it's a cash flow issue and a psychology issue. But I think ultimately it leads us to more flexibility down the road, which is why I'm making that recommendation for CalTech.
Great, that's helpful. Thanks, John. I don't know, David or Chris, did you have anything you want to add to that? No, okay. So Chris, there's a couple specific questions in the chat or in the Q&A, I'm sorry, about resolving some of the occupancy details. You're welcome to answer those live or in the chat. Or
I can sum those up pretty quick. So with the Wi-Fi data, we really were most interested in relating it to an air system, and so I did manually split buildings up based on where their air systems are and select the specific Wi-Fi access points in those buildings. Some buildings, it was really easy. You got an air handler for the first and second floor, and you got an air handler for the third and fourth floor. That's easy to split them up. Most of our buildings are split vertically, so you have like an east and west air handler, and that makes it, a lot more complicated. But in general, that was our interest. But then if it's a small building and it only has one air handler, then of course we're looking at the entire building. And so ultimately, we would like to get down to more specific area excuse me, more specific areas of the building. We're looking at conference room bookings through Google Calendar. Everything has to be reserved through Google Calendar, so we can look at some of those systems. But also, in terms of being able to do setbacks in our laboratories, we need to know that the occupancy sensors actually work. That's a longer term goal, is reducing our nighttime air changes in laboratories. And so those occupancy sensors are absolutely critical. And at this point, we still are really struggling to master the art of getting them working properly. That is something, there's another question about that as well. And the short answer is no, we haven't figured out a way to work around equipment that tricks occupancy sensors, but we are actively working on it.
Great, thanks, Chris. There was another question in the Q&A about anything that people have heard or research that's being done around detecting COVID from ceiling luminaire fixtures. And it says this would be beneficial for implementing at large facilities like Berkeley. So I guess there's a question around the ability to do this and detect COVID within a building through luminaires or otherwise. Is anyone familiar or have anything to share on that?
Very interesting question. I did a project in my master's program where we were doing fever detection with infrared cameras, and you have to have a pretty expensive camera to get enough resolution to really be able to pinpoint that. And I would assume that the sensors on a luminaire would be very low resolution. So that's just some thoughts on that. I haven't actually heard of anybody doing that.
Eric, I could jump in too, just to say we did, one of our researchers did sampling at the HVAC filters on air handlers, and just to see if they could find, virus RNA. There were some difficulties trying to identify that, but even with that type of sampling, you're not really identifying risk levels because you don't know if it's still viable. And a lot of the transmission is happening, probably almost all of the transmissions happening at room level. And so it can be a bit of a wild goose chase. That's a separate issue.
Not figured out quite yet. And I apologize. I want to go back to Bruce had a question, I think, on David's presentation, just the term campus emission electricity versus just campus electricity and how we're defining that.
Don't remember utilizing that term.
Okay, so that may just have been
maybe a misspeak on my part.
Okay, so we're going to say they're the same. Thank you. And we have a question from Selena, interested in how wildfire smoke is dealt with in operations and in design for new construction. So is it increased filtration, recirculation? How are folks dealing with that? So maybe John or Chris, I don't know, or Josh.
Yeah, this is in our newest building that we're in design right now. We're actually, this is a competition between this rising interest in indoor air quality, obviously COVID related, where you want airflow, you want 100% outside air to be, quote unquote safe. But then obviously living in LA on a regular day, there's air quality concerns. On a day impacted by wildfire smoke, there's severe air quality concerns. So yes, the short answer is we're dealing with filtration, but we're also working with JPL to develop air sampling in real time that would help us understand the outdoor air, the indoor air quality at the same time, and then modulate our filters. And so there are systems rather to optimize closing dampers or so forth, similar to what Chris has done with the Wi-Fi, connectivity to understand who's in the space. This is just comparing the outdoor and indoor data to see what's going on. It's in the nascent stages and we're piloting it in one building at JPL. But that this is going to be a continuing point of evolution and need in the mechanical systems going forward.
And I'll just add to that, it's also a huge concern for us at Berkeley Lab. We're very strongly affected by the smoke situations. We took kind of the opposite approach and started with just installing tons of air quality monitors. So we've got, between Purple Air sensors and another brand that we've used called E-Likens, we have about 90 of them installed across our site, both indoors and outdoors. Right now, with no intention of using that to automate anything, but to help us understand how our mitigation measures are actually impacting the indoor air quality. And those mitigation measures are bumping the filters up to MERV 13 or 14 filters, which has lots of implications and challenges, especially supply chain right now, and changing the recirculation modes on those units to anywhere we can to introduce the minimum allowable amount of outside air. So it's really just the combination of those two things. We're trying to understand how well they work so that we can make sure that we are making well-informed decisions. And now we are also implementing that in a separate project, implementing the modes in the air handlers so that we can, a single button click will allow us to shift the whole campus into a minimum ventilation mode when that happens.
I would also add briefly that we've all demonstrated work from home works. So one of our plan and our wildfire plan is actually to send people home, assuming obviously it's safe where they live, but get them off campus. Great.
Thanks for that, and looking forward to the pandemic mode button and the wildfire smoke mode button. I think this next question is for John. For locations utilizing Bloom fuel cells, was the opportunity to use the waste heat a consideration in procuring the fuel cell at all, or Bloom versus others?
It was, in fact, and that's one of the reasons why we settled on Bloom, is because they don't have a lot of excess waste heat. It's a very low grade heat that's coming out. So that enabled us to place them distributedly throughout campus and not co-located with our infrastructure, heating infrastructure. But now that we're looking at heat recovery chillers and so forth, there is an opportunity to harvest that low grade heat, and something that we're looking at how we could integrate that into our overall system.
Great. And I think we have another question for John. Have you had challenges with establishing the roles within the organization for establishing thermal and ventilation requirements for each space and approving changes? And how are you addressing that? I'm sure that was a piece of cake.
You can imagine at any higher education institution, but particularly at CalTech, there are people on campus who think they know how to do your job much better than you do. Anyway, joking aside, it was actually a very cool process. We worked with some of our researchers that were using technology to measure methane trace gas in outdoor environments. They brought that equipment indoors, and we converted the protocol to test using methane trace gas as a proxy for a COVID respiration, right? And measure the airflow in spaces. And so we went around, developed this with the faculty, and then our HVAC technicians took it over and tested several hundred spaces on campus to identify an air change rate. And then working with the faculty and the CDC guidelines, we had set up a threshold and a protocol for 4 air changes per hour was where we needed to want to get to. And so then based on the number of air changes that we measured in the spaces with the methane gas tracing, we then said the occupancy can either be this number of people or for this duration. And we set those occupancy limits early in the pandemic. As we went forward, we then changed the air handling system or provide additional filtration or purification, in those spaces to bring some of the spaces that might have been at 2 or 3 air changes up to that 4 air change threshold, so we could use them more effectively. So I'm not sure we solved who's in charge and sort of that power dynamic, because it still exists. But I think the main message is that we all came together the operational side, the academic side, to find a very creative solution to this that also, most importantly, was based in actual measurement and data, so that it made our constituency, our campus community, very comfortable that we were doing our job as a facilities department to go above and beyond to protect their health and safety.
Yeah, that's impressive. It's a good model. I don't know if
there's
Chris,
a story. I can send a link out to the story that we wrote on our campus website about that individual study.
Yeah, that'd be great. I don't know if anyone has anything else they want to add. Looks like Chris took care of one of Dan's questions. We have another question from Dan. Do you have a good supply chain for hydrogen for the fuel cells? Any challenges you've overcome related to this?
So right now they're supplied by natural gas. Fuel switching is something we're looking at. In fact, we're going into a pilot project with Bloom to understand how we could create hydrogen on site. The efficiency of that process at this point makes it a challenge, right, from an economic standpoint, and just in general an efficiency standpoint. But that doesn't mean that it's not worthwhile to explore and figure out. So the hydrogen economy is, as we all know, is coming tomorrow. It's just when that today is that leads us to that tomorrow, right? So hopefully we'll get there.
I'm with you on that. Sam is asking if there have been any changes from ASHRAE in recent years or for the future to broaden acceptable design conditions that may allow for more opportunities for energy efficiency. And I would imagine as that relates also to recent COVID guidance and other air quality issues. Throw that out there to anybody.
ASHRAE is definitely grinding hard on this. We've done a lot of research with other engineering firms and working with ASHRAE to understand how this, because they are somewhat competing terms, right? As competing agendas, as Chris mentioned, right? We're trying to bring in airflow, and we've turned everything up. So our energy efficiency blew out the window long ago. But I think there is, I'm not aware, maybe there are others on the call, Josh or somebody else who knows more specifically, but I know this is a top priority and they're working very hard on it.
Yeah, and I've heard the same thing. I think it's kind of shifted everyone's paradigm. So we're all in the same boat.
Okay, I think we got about a minute left. So we have a question for Chris. What would your suggestion for approaching IT regarding the Wi-Fi data be? How were you able to alleviate their security and privacy concerns? Sounds like that was a big question.
Yeah, and I could talk about that for an hour. I wrote a 17-page paper about it. The quick answer is that the privacy implications when I was sharing this project with researchers were huge, because if they want to publish information based on this data, there's a lot more involved in making sure that we're not invading anybody's privacy. From an operations standpoint, it's less of a concern. We have to have a policy for who can access the data and how long it's retained, but the implications for using the data internally were far less significant than when it was being used for a research project. And please, if you want to talk about that, reach out to me. I'm also just going to really quick point out, Marco commented in the chat that the Count repository on GitHub is an open source repository that is anxious for contributors. And so they've implemented on two different platforms, two different IT platforms, but are very interested in working with people who want to develop it for new platforms or different end use applications.
Okay, I think we're just at time here. We have one final question for John. I know, Allie, if we have time. We do? Okay, great. Did you have any challenges in designating the local utility as the secondary backup power supply for the building you profiled?
Yes, massive challenges. We're a municipal utility, Pasadena Water and Power. So they still have a business model that is based on the commodity of selling electrons. Where we overcame that was through long conversations about the big picture of where we are headed as their largest utility customer. And so we have gone to great lengths to paint the picture and vision of where we want to go and how that is beneficial to them over the long term. We're going to have higher electrical demand. We want to partner with them on deferred maintenance, both on our side of the grid as well as their side. So it's very much looking big picture and not specifically at the fact that we put a fuel cell in that took a megawatt of their demand off. So that's a knee jerk for them. They fought very hard. In fact, they put in a prohibition on putting in fuel cells in the city shortly afterwards. So again, it's an ongoing challenge, but I'm confident that the long-term vision is in alignment. And so we just need to focus on that.
Great, thanks. Well done. We knocked out all those questions right on time. We have a 10-minute break here. I'll turn it back over to Ali. First, I want to just thank David, John, and Chris for that presentation and transition across from macro to building level. That was great, and I really enjoyed it. So thanks again to everyone. It was a great session.